Hello everyone, welcome back to the Avinash Explains Tech YouTube channel and our Microservice Masterclass series. In part 1, we understand fundamentals of event-driven architecture, events, producers, consumers, event brokers, topics, queue, and the overall communication flow we understand. But creating an event-driven system is easy. The real challenge is making it reliable enough for a production. For example, what will happen if database is updated but the event is not published? What will happen if the same event reaches a consumer twice? What will happen if we change the event structure and an older consumer cannot understand it? And how do we track an event when it travels through the multiple services? These are the problems we will solve in this video. We'll try to understand all of these points. In this video, we will understand what is eventual consistency, what is dual write problem, what is transactional outbox, what change data capture, change data capture, schema versioning, event replay and idempotency, observability, and production best practices. So let's start with the eventual consistency. Suppose a customer places an order. The order service creates the order and publishes an order created event. Correct? And now the inventory service receives this event and resolves the required product. But notice something important here. The inventory is not updated at exactly the same moment as the order. Meaning when the order DB database got updated, it is not updating the inventory DB at the same time, right? First, the order is created, then the event is published, and after that, event service receives and processes the event. Okay, so this may take few milliseconds or sometimes a few seconds. During this short period, the order service and inventory service may not have completely consistent information. This is called eventual consistency. It means the entire system does not become consistent immediately. However, if there are no failure, all services will eventually reach to a consistency state. Consistent state. For example, immediately after placing the order, the may status may be order created. After inventory is resolved, it may become inventory resolved. After the payment succeeds, it may become order confirmed. Therefore, in an event driven system, we should not always expect an immediate final result. In an event driven system, we should not always expect that immediate final result. Our APIs, user interface, and business workflow should be able to represent intermediate states such as pending, processing, awaiting confirmations, right? Now you got the understanding of eventual consistency. Let's understand the what is dual write problem. This is one of the most important problems in event driven architecture. When an order is created, the order service needs to perform two operations. First, save the order in database. Second, publish an event to a message broker. Fine. There are two separate write for two different systems. That is why it is called a dual write problem. Suppose database operation succeeds and the order is saved, but before publishing the event, the application crashed. Now the order exists in the database, but no event has been published. The inventory service will never reserve the product, and payment service will never start the payment process. Correct? The reserve situation can also happen. Sorry, the reverse situation also can happen. The event may be published successfully, but the database transaction may failed. Now, the consumer receives an event for an order that does not actually exist. This creates inconsistency, and we cannot easily include a database or message broker inside one normal local transaction. So, how we can make sure that business data and its event are always recorded together? This is where transactional outbox pattern helps. To meaning to solving the problem of dual write, we have transactional outbox pattern which help us. Now let's understand. In the transactional outbox pattern, the order service does not publish the order service does not sorry the order service does not publish the event directly to the broker. Instead, it writes two records into the same database. It writes two records into the same database. The order goes into the order table, and the event goes into the outbox table. Most importantly, both records are written inside the same database transaction. Okay, imagine the operation is like begin transaction, save the order, and save the order created event in outbox table, and then commit the transaction. If the transaction succeeds, both records are saved. If anything failed, both records are rolled back. Clear? This gives us a single transaction boundary. We can no longer have a situation where the order is committed but the event is completely lost. The typical outbox records may contain event ID, event type, order ID, event payload, creation time, publishing status. Right? A separate publisher then reads these outbox records and send them to event broker. Notice that the outbox pattern does not guarantee that an event will be published only once. If the publisher sends an event and crashes before updating its status, it may send the same event again after restarting. Therefore, duplicate delivery is still possible. We can solve that problem using the idempotent consumers. But first, let's understand how outbox records can be published efficiently. Let's understand the change data capture. One way to publish outbox event is to run a background process that continuously query the outbox table. One way to publish outbox event is to run a background job, a process that continuously queries the outbox table. This is called a polling publisher. It works, but frequent polling creates additional database queries and may introduce unnecessary delay. True, right? Another approach is change data capture. commonly called CDC. CDC. Every database maintain an internal transaction log containing its committed change. For example, PostgreSQL uses the write ahead log. MySQL uses binary log. A CDC tool reads this transaction log. When it detects a new commit record in the Outbox table, it converts that change into a event. It converts that change into an event and publishes it to the broker. Right? Debezium is a popular tool used for this purpose. Debezium is popular tool used for this purpose. The complete flow now became clear. The order service saves the business data and Outbox event in a one transaction. The CDC publisher reads and committed changes from the database log. Then it publishes the event to the event broker. Finally, inventory, payment, and notification service consumes that event. Because CDC reads committed database changes and uncommitted or rolled back transaction will not produce a valid event. Now let's understand the schema versioning. Event schema versioning. Events act as a contract between producer and consumer. Suppose the first version of our order created event contains event version 1, order ID and amount, and later the order service needs to include the consumer ID. We may create version 2 like event version 2, order ID, amount, and customer ID. Adding an optional field is generally safe because older consumers can ignore it. But imagine that we rename order ID and remove amount and change its data type. Older consumers may fail because they are still expecting that previous structure. True, right? Therefore, the event schema must evolve carefully and it follow few simple rules. Include a version in that event, prefer adding optional fields, do not suddenly remove or rename existing fields, make consumers ignore unknown fields, use a new version for breaking changes, maintain backward compatibility whenever is possible. For larger system, teams may use JSON schema, Avro, or Protobuf with a schema registry to valid compatibility before deployment. Now we understand what is the use of schema versioning. Now let's see event replay and idempotency. One major advantage of storing event in a durable broker is that we can replay them. Suppose we introduce a new analytics service and this service need data from order created during the previous 6 months. Instead of directly reading another service database, the analytics service can replay the existing order events and builds its own data. True, right? Replay is also useful when a consumer has a bug. We can fix the bug and process the old events again. But replay introduces another question. What happens when the same event is processed more than once? For example, if a payment event is processed twice, we must not charge the consumer twice. If an inventory event is processed twice, we must not reduce the stock twice. This is why consumers must be idempotent. Idempotency means processing the same event multiple times produces the same final result as a processing it once. Every event should have a unique event ID. Process Before processing an event, the consumer checks whether that event ID has already been processed. If it has, the consumer ignores it. If it has not, the consumer performs the business operation and records the event ID. The business update and the event ID should preferably be saved in same transaction. This protects the consumer from duplicate delivery as well as event redeploy as well as event replay. Now let's understand the observability. In the event driven system, one request may travel through the several services asynchronously. So, debugging it using the simple application log can be difficult, right? We need three important observability components: metrics, logs, and traces. Useful metrics includes event publishing rate, consumer processing rate, consumer lag, failure count, retry count, dead letter queue size, end to end processing time. Logs should contain identifiers such as event ID, correlation ID, order ID, event ID, consumer name, and retry attempt. The same correlation ID should travel with the event with the event across all services. This allows us to follow one order from order service to inventory, payment, and notification services. Distributed tracing provides an end-to-end view and help us identify exactly where the event was delayed or failed. Okay. Now let's discuss the some best practices which we should follow while designing the event-driven architecture. First, design for failure. Assume that consumers may crash, networks may fail, and brokers may become temporarily unavailable. Second, use retry with exponential backoff. Okay, instead of retrying it continuously and gradually increase the delay between, instead of trying continuously, we should gradually increase the delay between retries. For example, first retry in 1 second, second in 2 second, third try in a 4 second, fourth try in 8 second, something like that. Keep increasing. This is known as a exponential back of retries. The third, always create idempotent consumers because duplicate delivery is normal possibility. The fourth is use the DLQ. If an event continues to fail after multiple retries, move it to a separate queue for investigation. But creating a DLQ is not enough. We also need to alert and process the correct and replay those events. The fifth is define alert and service level objective for consumer lag, failure rate, processing rate time, and dead letter queue size. Finally, secure the system. Avoid placing unnecessary sensitive information inside the event. Protect the broker using authentication, authorization, and encryption. We should also perform centralized failure or chaos testing to verify that retries, recovery, and duplicate handling even actually work. Conclusion. Let's quickly recap the complete flow. The order service writes business data and Outbox event in the same transaction. The CDC publisher reads the committed changes and publishes the event to the broker. Inventory, payment, and notification services consumes the event idempotently. Schema versioning protects consumer from breaking changes. Re- Replay allow us to build data and recover from bugs and metrics. Logs and traces help us monitor to complete event journey. These patterns are what transform a basic event driven design into a reliable production ready architecture. That's all for this video. If you found this explanation useful, please like the video, subscribe to Avinash Explain Tech YouTube channel, and share it with anyone learning microservices and system design. Thank you for watching, and I'll see you in the next episode of our Microservice Masterclass. Thank you so much.